Hi, we're Blue Well Solutions, and we have designed a soil vapor extraction system for the Hardeman County landfill in western Tennessee. Our site contains 4 main disposal areas, and our project is focused on the largest, the north disposal area. The site consists of unlined trenches with 200,000 drums of pesticide manufacturing waste and is likely the largest landfill of its type. 95% of drums are estimated to have leaked. The north disposal area is about 20 acres and contains an estimated 10 million pounds of chlorinated volatile organic compounds, with carbon tetrachloride as the primary contaminant of concern, as it makes up about 95% of the VOC concentrations. The project engineers decided to conduct a soil vapor extraction to remediate the vadose zone and groundwater contamination on the site. Soil vapor extraction is a remediation method used to remove volatile organic compounds from contaminated soil. It works by creating airflow through the affected area using a vacuum pump connected to vapor extraction wells installed in the vadose zone. Our objectives are to design an SVE remediation system for implementation in the north disposal area with the drums left in place. The remediation goal is to reduce soil gas CVOC concentration by 97%. To improve the water quality and protect human and environmental health in the area. A pilot test was performed in the southwest and southeast disposal areas to determine feasibility parameters for SVE on this site. From this, a net reduction of 96.5% of total VOCs was achieved after rebound, and at a design flow rate of 125 standard cubic feet per meter, the radius of influence exceeded 100 feet, with an average vacuum of 4 to 20 inches of water. After the SVE treatment of the southern disposal areas, the carbon tech concentrations observed by groundwater wells down gradient from the treatment area decreased by 1 to 2 orders of magnitude, implying that SVE in the north disposal area would largely improve groundwater quality. For our design, we had a few main assumptions. The vadose zone is 90 feet, soil is primarily sand, and the viscosity of waste air is equal to atmospheric air, due to low concentration of contaminants relative to primary air constituents. This site is unique in terms of both its area and depth, with large concentrations of contaminants estimated throughout the 90-foot vadose zone. Because of this, we designed clusters of 3 SVE wells, each with a 20-foot screen across shallow, intermediate, and deep depths. The SVE well layout was determined based on a well cluster spacing of 125 to 175 feet to prevent competing vacuums, a radius of influence of 100 feet, and a total treatment area of 29 acres. Figure 8 shows the well cluster layout as well as the radius of influence of each well cluster. Our treatment design consists of determining the treatment plant location and representing the air and condensate treatment systems in a process flow diagram. The selected treatment plant location was in the bottom left section of the area as shown. This area was selected due to its relatively flat topography and its central location relative to each third of the treatment area. This is the process flow diagram for the treatment system. First, contaminated air is drawn through the extraction wells and carried to the treatment plant through a piping manifold. Then the flow is divided into quarters to flow through 4 knockout pots in parallel, which separate the air from the condensate. The condensate is treated using a granular activated carbon absorption system designed in a lead-lag configuration to ensure sufficient contact time. Next, on the air side of the knockout pot, a large blower generates the vacuum that extracts the vapor from the ground and moves it through the treatment system. Highlighted is the selected air treatment system, a regenerative thermal oxidizer. When selecting the air treatment system, alternatives such as granular activated carbon and catalytic oxidizers were considered but rejected due to their risky reactions with chlorinated compounds like our main contaminant of concern, carbon tetrachloride. The final step in our treatment process is a wet scrubber that neutralizes the hydrochloric acid produced by the thermal oxidizer before releasing the clean gas into the air. In order to monitor and optimize the system, nested vapor probes were designed. These probes allow for monitoring vacuum and VOC concentrations at various steps in places other than the SVE wellheads. For these, 4 probes are screened at various depths and connected back to the surface with a 1/4-inch PTFE tubing to allow for sampling. The depths that the probes are screened at was designed to provide the most information on subsurface behavior during venting using the fewest wells. Therefore, one probe was placed at the top and one at the bottom. The lower middle probe is placed halfway between the lower and middle screens to monitor for vertical stagnation due to competing vacuum. The upper middle probe is placed halfway along the middle screen to monitor where there should be no competing vacuum. The nested vapor probes are divided into two groups, on and off cap. The off cap group is relatively evenly distributed about 20 to 30 feet away from the outer radius of influence. These probes are primarily intended to ensure that the plume does not spread unexpectedly beyond expected boundaries. The on cap probes are placed in areas where the radius of influence overlaps to monitor and optimize removal. Thank you.